Hello, Professor.
Hey, Lewis.
I
Oh,
have a
Lewis, can you hear me?
question. Yeah, I can hear you.
What's up?
So we're doing the research paper on surgical reconstruction,
Uh-huh.
and well, I'm kind of confused how you want us to do like an analysis of that.
Um, yeah, so so the analysis should be something like like the calculations we've been doing in class. I think for you
Mhm.
guys, I'd be interested in seeing, if for a limb or whatever that's been surgically reconstructed, just maybe doing analysis on that in terms of what are the forces required in the reconstructed limb, or maybe if it's like an internal part, like what are some, like usually when you have something surgically reconstructed, the doctor recommends you to like not do certain actions, right? Because it kind of
Yeah.
puts you at risk of kind of re-injuring yourself or kind of reopening a wound. And so maybe doing an analysis of those kinds of actions to see, what kind of, how much force could you really sustain in a situation like that without, potentially hurting yourself or reopening a wound or something like that.
Okay, so more like so like I ended up switching up like a paper of like a runner that had his foot amputated or his
Yep.
leg amputated, but that would be more prosthetics, right? Instead of actual surgical reconstruction.
Yeah. So what kind of surgical reconstruction did you guys have in mind?
Well, I don't think we've like narrowed down to a topic, so we're just kind of searching up a lot of different areas. But I guess I wanted to ask like if someone did something like where they got amputated and they had like a replacement, would that still count, or would that be completely into prosthetics? Because it
No,
kind
yeah,
of
that
like
no, that would count. So right now there's no group that's doing prosthetics, and so you guys can definitely get into that area.
oh, so even though we're surgical reconstruction, if we got into prosthetics, like talking into it, or we would have to completely switch over to prosthetics.
No, no, you can. Yeah, you don't have to switch over to it. You guys can kind of be at the intersection in between those two. So you can do
Okay.
maybe some prosthetics and some reconstruction of maybe something internal, and then maybe some actions that would put such a person at risk. Yeah.
Okay then. Okay then. I'll think on that. And then tomorrow you have office hours, correct?
Yes. Yes.
Okay then. I'll come to you with more questions.
Okay. Yeah. I think that sounds good.
Okay. Thank you, Professor.
Yep. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Everyone have a good Thanksgiving break? Busy, I'm sure. Thanksgiving is always at the worst time. It's the end of the semester, so I know probably a lot of you guys were working and busy and stuff. But now that we're back, we have 2 more weeks to go. At least 2 more weeks of lectures. So we have 2 lectures this week and 2 lectures next week. But of course, next week we also have final presentations. And so actually today's the second to last day you're going to be hearing from me. So we're gonna have a lecture today and a lecture on Wednesday, and then that's it for me. And then all of next week we'll be just focusing on final presentations from there. Okay. And so with that said, we are in kind of the very late stages of the class. And so I just have one more topic that I want to go over, which is muscle force optimization. Which that's all I have planned for this week. So I have one example that we're going to do today, and then one example we're going to do Wednesday, and then that's going to be it. Okay. And then next week is going to be all final presentations. So I've made the schedule for the final presentations already. So basically the final presentations are going to be split. We have 8 groups in total. So 4 groups are going to go on Monday and 4 groups are going to go on Wednesday. So I'm just kind of at the stage where I'm just kind of formatting the final presentation schedule. So I'll send that out to everyone today. So make sure you read the schedule to make sure that you know whether it's going on Monday or Wednesday. Okay. Okay. So what I want to do today is I wanted to go over together with you the rubric that I'm going to use to grade your final presentation. So that's been on Canvas for the last few weeks, but I did want to go over together to kind of talk to you in terms of what I'm looking for, in terms of how you should structure and organize your presentation. Okay, and then from there we'll move on to the final topic, which is muscle force optimization. Okay, so there's no more homeworks in this class. The homeworks are completely done. The last two things that you have to do for this class, before we let out for break, is just one, the final presentation, and then two, the final report. Okay, so those are the last two things you have to worry about. I've also graded your midterm exams, so I finished grading those on Monday during the break, so I have those with me right now. So I'll give those out after the class today. I actually didn't even check what the average was on the midterm exam, but it looked pretty similar just visually compared to the first midterm. So overall, you guys did really well. Okay. All right. Any questions I can answer before we get started for today? Yeah.
The finals, are you gonna have regular office hours or
it'll be a little bit different. So usually for finals week, I do office hours mostly by appointment. And so if you want to make an appointment, just let me know. But if there's enough demand, then I'll probably just open it up to just general office hours, and because my schedule for finals week is usually a bit different, because that's when I usually do kind of more kind of graduate work, research stuff. So I probably need to move office hours around. So if there's enough demand, then I'll probably open up general office hours. Yeah. Mm-hmm. Okay, all right, so first thing we're gonna do today is let's go over the rubric for the final presentation, okay? So final presentations are gonna start next Monday, right? Okay, and so here is the rubric that I'm gonna grade you on next week. Okay, so the presentation, of course, this is a group presentation, so this one rubric is gonna apply to everyone in your group, okay? And if you're wondering where to find it, if you go to the assignments tab in our class, if you go click on final presentation, the only file that I have here is the rubric, okay? Okay, so you can see the rubric is broken down into these sections. And so there's 4 primary sections I'm gonna grade you on. So the first being the introduction, the second section being the biomechanical analysis, the third being the discussion, and then the conclusion, okay? So generally, I would like your presentations to be organized in this manner. And so starting with the introduction, and so with the introduction, basically, I want you to describe basically all the relevant background information on the topic. So for a lot of your topics, especially, so this year in particular, a lot of you guys picked some really interesting and kind of more kind of specialized kind of niche topics. And so, I really want the introductions to be kind of really, pretty clear, okay? And generally the mistake that I see the most that people make with their introductions is that, I know you guys, probably over the last few weeks been reading papers, doing research on the final topic, or, at the very least this week, you're going to do some very intense research and looking into your final project topic. And so when you're introducing this, you should always kind of keep in mind that the people that are reading your introduction, people that's listening to your introduction, are kind of hearing about your topic for the first time. And so you want to make sure you kind of start, you kind of start from a starting point that's kind of, easily graspable by a general audience, and you kind of, more kind of get more specific from there. The analogy that I always like to think about when I'm writing introductions, and this is what was taught to me in grad school, and I think it's applied here. Think of your introduction almost like a funnel. And so at the top of the funnel, the very beginning of your introduction, you should start kind of very broad and very general, because that's kind of what the general population generally understands. And then as you go through your introduction, you kind of funnel your way down to kind of your specific topic from there. Okay, so it kind of gives like a nice buildup, a nice kind of introduction to your topic. And I think what's most important about the introduction is that you should really illustrate, or you should really kind of communicate to the audience why your topic is something that's important to study for biomechanics. Okay. So those are kind of the two main things that I'm looking for the introduction. One, is it easy to follow? Is it something that kind of has a very logical kind of progression in terms of starting general, getting more specific? And two, does it provide enough motivation in terms of, why this is an important topic for biomechanics and why people are studying it, and why, it's something that, can lead to general improvements to kind of, human health. Okay. All right. And of course, the introduction should also place your topic within the context of the class itself, right? So it should also kind of, talk about, you should also kind of mention some of the things that we've talked about in the class and how that relates to your topic. Okay. So the introduction is worth a pretty decent chunk of points. So I do rate the introduction pretty highly for this project. So, make sure you do a good job for that. Okay. All right, so the next section is the biggest chunk of points on the presentation, which is going to be the biomechanical analysis. Okay, so this is what we talked about when we first introduced the final project. That a big portion of your final project is going to be, applying the methods, applying the the calculations that we've done in the class to your specific topic. Okay, and so we went over. So this rubric's a little bit outdated. So we didn't get a chance to go over biomechanics of balance, although it's kind of just a subset of static analysis. So. You should have at least 2 biomechanical analyses in your presentation. So they could either be static analyses or dynamic analyses. Okay. And so, think of these as almost like example problems that you're going to be presenting to the class. So, you should show me all the relevant diagrams, at the very least a free body diagram that kind of, shows all the forces that are accounted for and justified. Okay. You should show all the governing equations, derivations of the governing equations, and all the worked out algebra as needed for your problem. Okay, and all the solutions to these problems should also be correctly computed as well. Okay, and of course, exactly what solutions and what equations you're going to use are going to depend on whether you're doing a static analysis, dynamic analysis. It's all going to depend on that. But it should be a fully worked out problem. Right? And so you should have 2 of them in your final presentation. Okay. Your final report should have 5 analyses in total, but for your presentation, due to kind of just the time constraints, I'm only going to look for 2. Okay. Okay. And so the next section is a section called discussion. Okay. So discussions, it's an important section as well. And so in the discussion section, what I'm looking for is to kind of take the results of what you obtained in your biomechanical analysis and basically discuss them and analyze them and kind of talk about why they're important to your topic. Okay. And so the way I kind of see this is that, in the biomechanical analysis, you're primarily just doing computations. In discussion, you're kind of discussing why those computations are important, why they're relevant. Okay. And so let's say that, I'm just going to use one group as an example. So let's say that, you're doing the biomechanics of lifting. Okay. And so maybe, during the biomechanical analysis section, you computed a certain amount of muscle force, a certain amount of joint reaction force that's associated with maybe a certain lifting technique. Okay. And then in the discussion section, what I would be looking for is, talking about why that amount of force is significant, right? So maybe that amount of force commonly will lead to injury. Maybe that amount of force is good, right? Maybe you want to redirect the force in a certain direction, right? And so, in the discussion section, you have to talk about kind of why that result is important. Okay. And so this is kind of where you kind of bring in some information from the introduction, and you kind of combine that together with your analysis to kind of give a full picture in terms of, the analysis and why it's important and why it's relevant. Okay, so don't skip out on the discussion. So I think, a lot of for in the past when I've offered this project, a lot of people kind of skip the discussion. They just show me the calculations, and then there's really nothing in terms of discussion. So make sure you have that there. Okay. The last section I'm looking for is the conclusion, and so the conclusion is usually just a single slide. And so usually for a conclusion for a presentation just kind of provides a very nice and concise summary of the entire presentation. Okay, and so it summarizes kind of the most important points of the introduction, summarizes a little bit of the analysis, and summarizes a little bit of the discussion. Okay. Conclusion is usually the easiest part. So, that's usually just one slide. Okay. Okay. And so the last couple factors here, they're not specific sections of your presentation, but I am going to be looking at them. And so the first being the presentation aesthetics, right? And so the presentation should be cleanly organized. It shouldn't just be kind of thrown together at the last minute. So there should be, proper grammar, proper spelling, proper capitalization. the text and figures are easy to read. Okay. And usually for the aesthetics, what I'm looking for is a lack of clutter. And so typically what I see in a lot of presentations is I just see kind of like an essay on the screen, right? And so that's usually not usually doesn't make good for a good presentation slide, because usually for a presentation slide your audience is only going to be looking at it for maybe a minute or two, and so they're not going to have time to read an entire paragraph worth of information, right? And especially considering they're going to be listening to you talking at the same time too, and so it's impossible to kind of read a long block of text and listen to someone talk at the same time. And so usually what I tell people for presentations is less is more. And so the less text that you can put on the slide, or even better, if you can just show a figure and then just talk about the figure and kind of have that kind of memorized from there, that would be kind of the best way to do that. Okay. And then the last section is presentation skills. And so, make sure that you have a clear voice, make sure that, I can hear you. And most importantly, stay within the time. Okay. So since we only have 8 groups this year, you do have there is a little bit more flexibility with the time. I think in the project specs, I think I told you 12 to 15 minutes, but you actually have a little bit more time. So you have between 15 and 18 minutes. Okay. If it's less than that, that's fine. But the most important thing is that we kind of stay on schedule so everyone has a chance to present. Okay. And so kind of the most important thing for here is to make sure you rehearse your presentation, make sure you deliver what you need to say. Okay. Because usually what I find is that when students give presentations, it's not really the amount of content that gets people to go over. It's kind of a lack of practice. And so, people spend a lot of time saying, they kind of fumble around with the index cards a little bit. And so, practicing your parts and making sure you're saying it, without any kind of dead time, that's kind of the thing that kind of helps you stay within the time. Okay. Okay. So that's kind of the rubric for the final presentation. Okay. Any questions on this rubric here? Okay. All right. So final presentations are going to take place Monday and Wednesday of next week. I am considering just having both the lectures next week be virtual, so we can just deliver the presentations on Zoom, just to kind of help you out, just because I know it's kind of a lot of information to kind of process. So if you have it in front of your computer, it's a little bit easier. But I'm still kind of debating at this point. But I'll send an announcement if I do decide to go that route. Okay. Okay. All right. So that's it for the final presentation. So let me go ahead and bring back the iPad here. Okay, so let's go ahead and continue the topic that we left off on before Thanksgiving. It was a long time ago, so I'm definitely going to summarize a bit of what we talked about. And so the topic that we ended on was one called muscle force optimization. Okay. Okay. Oops. Don't know why the Zoom is frozen here. Sorry about that. There we go. Okay. Muscle force optimization. So muscle force optimization, this is kind of the last stage of kind of dynamic biomechanical analysis. Okay. So of course, there's going to be no homeworks on this topic, and there's all the midterm exams have passed, and so I'm not going to test you on this. But the reason I kind of saved this topic for the last in the class is because this is something that's typically good to use on your final project. So I think last year, I think maybe about half the groups used some kind of optimization on their final project. Okay. And the goal with muscle force optimization is to take a dynamic scenario or take a dynamic motion and compute the exact amount of forces each muscle is exerting to accomplish that motion. Okay. Okay. Because we've been kind of going over a kind of a 3-step process, you know, up until this point, right? And so the first being you know, motion capture or kinematics. Okay. And so remember the point of motion capture is to take a motion and kind of quantify that motion or record and you know, get the data for a certain motion, right? And so that takes the form of the joint angles, the joint velocity, joint accelerations as a function of time. Okay. Step 2 is inverse dynamics. Okay. And so the point of inverse dynamics is to take that kinematical you know, data and convert that basically into net forces and net moments at the joints, you know, for a person's body. Okay. And then what we're on here is the muscle force optimization. Okay. And so the muscle force optimization, what that does is that, you know, from the inverse dynamics, right? What you're going to get from inverse dynamics is that, you know, at all the particular joints in a motion, so let's say the knee joint, the ankle joint, the hip joint, you know, you have a net amount of moment and a net amount of force that needs to occur, right? It then takes that information and then translates that to, all right, what are the individual muscle forces that can contribute to this? Okay. So let me kind of illustrate to you kind of what this looks like. Okay. And in fact, you know, I think this would be kind of a good transition into the example that we were going over. Okay. So let's say that we're interested in the muscle forces that are required to accomplish a plantar flexion action in your ankle. And so remember, a plantar flexion moment, remember, that's basically the moment that drives your foot into the ground, okay? And so let's say that we have your foot here. Okay. And so a net plantar flexion moment is going to go in that direction, okay? Okay, and so let's say that the moment here, okay, the net moment that's at the ankle joint that we obtained from our inverse dynamics analysis is 100 Newton meters. Okay, so this is right here, the net moment at the ankle. Okay, this is the net moment at the ankle that was obtained via inverse dynamics. Okay, all right. And so at the ankle, we have 3 muscles that are active. Okay? In particular, these three muscles all have the ability to produce a plantar flexion moment. Okay, so one, we have the gastrocnemius. Two, we have the tibialis posterior. And three, we have the soleus muscle, okay? So all three of these muscles are in your calf. So they're kind of in the back of the lower leg, okay? So these three muscles kind of typically comprise the calf muscle, okay? Okay. And so one thing that we'll specify here is that each of these muscles have a maximum amount of force that they can exert. Okay, because remember when we were talking about kind of muscle biomechanics, you know, each muscle has its own kind of cross-sectional area, which determines how many sarcomeres and how many muscle fibers it has in parallel. Okay, so since each of these muscles have a different size, you know, they each have a maximum amount of force that they can exert. Okay, and so for the gastrocnemius, its maximum is 4,097 newtons. Okay. For the tibialis posterior, the max it can do is 3,052 newtons. Okay. And then for the soleus, the max amount of force that it can do is 6,435 newtons. In addition to the maximum force, you know, what we can also measure the moment arm between these muscles and the ankle joint. Okay, because remember, you know, in order to produce a moment, you know, we take a force and we multiply it by the moment arm, right? And so based on measurements or based on where these muscles attach relative to the ankle, we can compute their moment arm as well. Okay, so for the gastrocnemius, its moment arm is 3.9 centimeters. Okay, for the tibialis posterior, its moment arm is 0.8 centimeters. Okay, and then for the soleus muscle, its moment arm is 3.6 centimeters. Okay. Okay, so let me kind of illustrate this. Let me kind of illustrate this for you. Okay. So I'm going to draw kind of a very simple diagram, just to kind of make it simple, right? So let's say in 2D, this dot right here represents the ankle joint. Okay. First, let's look at the the gastrocnemius muscle, right? So let's say the gastrocnemius muscle attaches, you know, somewhere over here. Okay. And then produces a force Fg in that direction like that. Okay. This Fg has a maximum of 4,097 newtons. That's not to say that it has to produce 4,097. That's just the max that it can produce. Okay. And then this moment arm right here, or the distance, the perpendicular distance between Fg and the ankle joint, this right here is 3.9 centimeters. Okay. Next, let's draw the tibialis posterior. So let's say the tibialis posterior is something like this. Okay. So I'll call this FT. Okay. So I'm exaggerating the positions a little bit just to make it easier to see. In reality, you know, these are going to overlap a lot more. Okay. So FT is something like this, and its moment arm, or the perpendicular distance between the FT vector and the ankle joint, this is 0.8 centimeters. Okay. And then finally, the soleus muscle, let's say that it's kind of right here. Okay. We'll call this FS. Okay. And then its moment arm, which is again going to be the perpendicular distance between the soleus muscle and the ankle joint. Okay. This is going to be 3.6 centimeters. All right. So I drew it like that. I kind of separated all the muscles out just so that you can see each one. But in reality, it's a little bit more stacked because some of these muscles, they may share the same tendon and attach at the ankle in the same way. But so there's a lot of overlap, but I kind of separated like this just so you can see. Okay, so based on this diagram and kind of based on what we know about moments around a joint, we can write a formula for the total amount of moment that these three muscles produce around the ankle joint. Okay. Okay. Okay, so the sum of the moments around the ankle joint, all this is going to be just going to be the product of the force multiplied by its moment arm, all added up together. Okay. Okay, so we have FG. Okay. We're going to multiply by its moment arm, but we're going to convert the moment arm to meters as we typically do. Okay. So it's going to be FG times 0.039. Okay. Plus FT multiplied by its moment arm. So its moment arm is 0.8 centimeters. And so convert that to meters, that's 0.008. Okay. And then we have the contribution from the soleus force, okay, which is Fs. And then we're going to multiply by this moment arm of 3.6 centimeters, which is 0.036 centimeters. Okay. I know that each of those moments that I've shown in the figure there produces a clockwise moment. And typically for clockwise moments we make a negative, but since they're all just kind of going in the same direction, I'm just changing their sign to positive in this case. Okay. But you can very easily just make them all negative as long as all three of them are the same sign. Okay. Okay. So that's the sum of the moments, right? If this were a static problem, we would set this equal to 0, right? But this is not static. This is a dynamic problem. So we have a net moment at the ankle joint. Okay. And in fact, we were given it in the problem. And so that net moment is going to be 100 Newton meters. And so we're going to set this equal to 100 Newton meters. Okay. So this was given to us in the problem. All right. So that was a long setup of the problem. Okay. So what are we looking for here? So what we're looking for here is we want to solve for all three of these muscle forces. So we want to solve for FG, FT, and FS. Okay. So we want to compute. The optimal the optimal distribution of muscle forces and so that's values for FG, FT, and FS. Okay. That we need to complete this motion. Okay. This motion being, producing that net moment of 100 Newton. All right. So we have three unknowns here, right? So we have three unknown muscle forces. So we have FG, FT, and FS. Okay. All those are unknown. But so far, we only have one equation, right? So we only have our one constraint equation. Okay. Okay. And so, pretty much all optimization problems kind of fall into this category when you have more unknowns than you have equations. Okay. And so in these situations, you can't solve for your result. You can't solve for your answer in kind of the traditional algebraic way. Okay. And so in order to get a solution from this, we need to solve it through optimization. Okay. All right. And so, of course, in the two lectures that we have left, we don't have enough time to go over, everything about optimization, right? And so if you're in 454, we've spent the entire semester talking about optimization, and we're still, always kind of scratching the surface. And so in two lectures, we're definitely not going to be able to do that. Okay. The good thing about optimization is that it is a fairly common task that you're going to have to do in engineering analysis in general. And so there are a lot of kind of pre-packaged routines and pre-packaged functions that you can make use of in MATLAB and Python, in basically any programming language. And so the focus that we're going to do in this class is to basically say, how can we use one of these pre-packaged routines to solve a problem like this? Okay. Okay. And if you're curious about the specific routine that we're going to use, it's called fmin-con. Okay. So what that function is short for is F. F stands for a function, right? And so that's what we're going to minimize. Min stands for minimize, and the con here stands for constraint. And so essentially, we're going to run a constrained optimization on this problem. Okay. And for those of you in 454, the exact routine that's actually used here is a constrained version of Nelder mean. Okay. But if you're not in 454, don't worry about it. That's just a little trivia for those students, because I know there's some overlap. Okay. Okay. So the question is, how do we set up an optimization problem to use in MATLAB? Okay. And so to use an optimization routine, kind of your mindset kind of shifts a little bit, right? I think kind of traditionally what you're used to when you're given an engineering problem to solve or engineering analysis to do is, you kind of focus more on kind of the steps or the routine to actually solve for the solution. Okay. When you're using a prepackaged routine in MATLAB or a prepackaged algorithm, the computer is going to do all of that kind of work for you. What you're going to do instead is you're going to just simply set up the problem. Okay. Okay. Which sounds easy, right? So this sounds like something that's easy to do, but for a problem like this, it's actually a lot more complicated, and there's a lot more steps to it than you may think. Okay. And so usually when you set up a problem, basically what you have to do is you have to define all the different parts of the problem as it relates to your original problem. Okay. And so for an optimization problem, there are three main parts that we have to kind of define. Okay. And so, first thing we're going to talk about is, how do we define these parts just in general? Okay. And then we'll talk about how do we actually implement these parts in the code. Okay. And so the three parts that we have to decide here are, one is going to be the design variables. Okay. We've actually done this already. And so this is already done, but it's just kind of being more kind of clear and specific about it. Okay. Two is going to be the constraints. Okay. So we'll talk about what that means in a second. And three, the last thing that you have to define in an optimization problem is something called the objective function. Okay. So we're going to define all three of these things. So 1 and 2 are actually already defined to us in the problem. 3 is the only part where you have to use a little bit of creativity and a little bit of kind of intuition in order to come up with something like that. Okay. Okay, so let's go through each of these parts individually and talk about kind of what they mean and what they actually are for this particular problem. Okay, so one, let's go over the design variables and what that means. Okay, so the design variables, these are essentially the unknowns in our problem. So these are the things that we want to solve for solutions. So i.e. Okay. So these are the things that we want optimized. These are the things that we want to solve for in the problem. Okay. And so in this problem, we already know what these are, right? So these are going to be the 3 muscle forces that we don't have values for. Okay. So this is FG, FT, and FS, right? The muscle force for the gastrocnemius, the muscle force for the tibialis posterior, and the muscle force for the soleus muscle. Okay, 3 unknowns, and those are our 3 design variables. Okay. All right. Another thing that's usually defined at this stage is the maximum and minimum values, allowable values for these muscle forces. Okay. So we already know the maximums, right? So that was given to us in the problem. So each force has a maximum amount of force that they can exert, right? So for FG, we know that FG has to be less than 4,097 newtons, okay? FT has to be less than or equal to 3,052 newtons, okay? And Fs has to be less than or equal to 6,435 newtons, okay? So those are the maximum values. Okay. These also have minimum values as well, right? Because we know that the muscle forces cannot be negative, right? Muscle forces can only exert tension. It's impossible for them to kind of compress on themselves, okay? And so we know all these have to be greater than or equal to 0 newtons as well. Okay. All right, so those are our 3 design variables and their 3 ranges, okay? And so what this is basically telling us is that, you know, throughout the optimization, you know, what we're going to solve for FG, FT, and FS, you know, ideally their optimal values are going to be within these ranges. Okay. All right, any questions on this so far? Okay. All right, so those are the design variables. And so, you know, I know all of that was given in the problem, but, you know, when we're setting up the problem, you know, we have to be kind of clear and specific about these things. Okay. All right, so number 2 are the constraints. Okay. All right, so the way that you can think of constraints, so just like the name implies, these are basically things that are going to constrain the values of our variables here, okay? So the constraints, you can think of them as mathematical relationships between the design variables that must be satisfied, that must be kept by the optimal solution. So you can think of constraints as kind of equations that have to be satisfied by whatever your solution is going to be. Okay. All right, so we have one constraint here, okay? Because what we know from the problem is that these combination of muscles, you know, from our inverse dynamics analysis, they have to produce a net moment of 100 Newton meters. Okay. All right, and so we had an equation for that as well. And so we had basically each of the forces multiplied by their moment arm. So we have 0.039 multiplied by Fg plus 0.008 multiplied by Ft plus 0.036 multiplied by Fs. Okay. This has to equal 100. right? So whatever combination of FG, FT, and FS that we obtain from our optimization algorithm, it has to satisfy this equation right here, okay? This type of constraint here is known as an equality constraint because it's an equal sign relationship, okay? There are such things in optimization called an inequality constraint, where instead of an equal sign, you have like a less than or equal to or greater than or equal to. And there are ways to kind of implement this in the code as well. But I think for now, we'll just focus on equality constraints. Okay. Okay. So as far as constraints go, that's all we're given in the problem. So that's all that we can do. Okay. Any questions on this? Okay. All right. So after constraints, the last part of an optimization problem that we have to define is the objective function. Okay. So this is the only part of the optimization that's actually not given to you typically in a problem. Okay. All right. So the purpose of the objective function is basically to give us a means or give us a way to differentiate what are some good solutions and bad solutions. Okay. And so to kind of understand the purpose of the objective function, it kind of helps to kind of think about kind of what an optimization algorithm is going to do. Okay. Essentially, an optimization algorithm is basically going to be like an educated guess and check. Okay. And so what the computer is going to do is that for your three variables here, so FG, FT, and FS, okay, what the computer is going to do is that it's going to produce, seemingly random guesses, although, most time it's not completely random, right? It's going to produce guesses for these three variables, and then it's going to test and see, which combination is better than the other ones, okay? So essentially, maybe we'll have guess one right here. Okay, so maybe we have FG1, FT1, FS1. Okay, so those have their values. Okay, versus guess two, and we have FG2, FT2, and FS2. Okay. And so let's just assume that both of these guesses satisfy the constraint. Okay, so both of these are equally valid. Okay. And so if both guesses satisfy the constraint, then are we going to say that both guesses are valid, right? Or are both guesses good? And so we have to have a way to basically differentiate between which is better between guess one and guess two. Okay. And usually there is some criteria, based on kind of the mechanics and based on the physics of your problem to tell us that, whether one guess is better than the other ones. Okay. Okay. And so that's essentially the role that the objective function plays. So the objective function is usually just one function, which mathematically gives us a way to say which solutions are better than others. Okay. Because when you have an under constraint system, and essentially this is what it is, right? We have more unknowns than we have equations. There are an infinite amount of solutions that can satisfy that system, right? And so when you have, three unknowns here, right? We have FG, FT, FS, and we only have one equation here that kind of constrains their values. We have an infinite amount of combinations of FG, FT, and FS that satisfy this criteria here. Okay, but some of those guesses out of the infinity are going to be better than the others. Right? So the objective function gives us a way to determine that. Okay. So the objective function So the objective function gives a way, for the optimization algorithm to determine which solutions are more optimal than the others. Okay. The key to this definition are these two words, more optimal. Okay. And so this is where you have to use a little bit of kind of intuition and a little bit of kind of knowledge in the exact field to kind of determine, how do we define what makes something more optimal than the others? Okay. Because there's a lot of ways that we can use. There's a lot of ways that we can define, some solutions be more optimal than the others. Okay. Okay. So for example, let's kind of bring it back to this specific example for our three anchor forces, right? So there are a lot of different objective functions that we can use. Okay. So let's say that we are going to use an objective function that aims to minimize the total amount of force that's exerted at the ankle. Okay. Okay. And so our objective function here is total amount of force, right? And so if we sum up the amount of forces, right? And so this is just going to be the sum of the force magnitudes. Okay, maybe I should indicate that. Okay, because of course, each of these forces have their own directions, which normally need to be accounted for. But if we just sum up their magnitudes, okay, then we just have a sum of Fg plus Fs plus Ft. Okay. And what the objective function is going to do, or what the optimization algorithm is going to aim to do, is it's going to find optimal solutions that satisfy the constraints that minimize this particular function. Okay. And so a solution is going to be deemed more optimal than another if it minimizes this function. Okay. Okay, so let me write our constraint again here, and let me kind of show you a couple of examples, right? So we're going to do a couple of valid solutions, and you're going to see which ones are going to be more optimal than the others based on this objective function. Okay, so our constraint here is 0.039 Fg plus 0.008 FT plus 0.036 FS. This has to equal 100, okay? So this is our constraint. So this has to be satisfied by our solution kind of no matter what, okay? So let's go through a couple scenarios here. So a couple scenarios of valid solutions, okay? So let's test the solution where, you know, let's say the tibialis posterior muscle is doing all the work, okay? Okay. And so the tibialis posterior is going to do all the work. That means FG is going to equal to 0 and FS is going to equal to 0. Okay. And so if that were the case, then our constraint equation here simplifies to 0.008 FT is equal to 100. Okay. And so through our assumptions here, we were able to eliminate 2 of the unknowns. And so that leaves us with just one equation here. Let me pull out my calculator really quick. And so if we solve for FT here is just going to be 100 divided by 0.008. Okay. So FT in this case will be 12,500 newtons. Okay. All right. And so, of course, you know, if you kind of remember our design variables here, you know, that of course violates the maximum. So technically, this is not a valid solution, but we'll assume that this is valid for a second. Okay, so we're just illustrating the objective function. Okay. All right. So let's compare that to a solution where, let's say, instead the gastrocnemius is going to produce all the work. Okay. Okay. So FT is going to equal to 0 and FS is going to be equal to 0. Okay. So in that case, we have 0.039 FG is equal to 100. Okay. And so we solve for FG. And so we solve for FG in this case, we take 100 divided by 0.039, and what we get is 2,564 newtons. Okay. All right. So both of these solutions here accomplish our constraint, right? So both of these solutions will give us, you know, 100 Newton meters of moment around the ankle, right? Okay. And so technically, you know, since both of these satisfy the constraint, they're both going to be valid. But one of these solutions is more optimal than the other, right? So if we look at our objective function here, right? So our objective function in this case is just the sum of all the forces. So we have FG plus FT plus FS. Okay. If we evaluate this objective function, there are 2 solutions. So for solution 1, okay, solution 1 was the case when the tibialis posterior muscle does all the work. Okay, we have F, little f in this case, the objective function is equal to 12,500. Okay, whereas for solution 2, okay, solution 2 is the case where the gastrocnemius does all the work. Okay, and so in solution 2, our objective function in this case is 2,564. Okay. And so in this particular case, for this particular objective function, it should be pretty clear which one is more optimal, right? Because we always want to minimize our objective function. And so the case or the solution with a smaller objective value is solution 2. So solution 2, this one is going to be more optimal. Okay. And so without the objective function, we wouldn't be able to determine, which of these solutions are more optimal, because technically both of them satisfy the requirements, both of them satisfy the constraint, but one is obviously much better than the other ones because it minimizes the total amount of force. Okay, so that's the purpose of the objective function. The objective function is to help tell us, which solutions are more optimal than the others. Okay, and the tricky thing with the objective function is that you often have to use a little bit of intuition, a little bit of kind of background knowledge to write a good one. Okay. All right. Any questions on this? Okay. All right. So those are the 3 parts that we have to define here for the optimization. Okay. Like I just mentioned, the trickiest part here is the objective function, right? And so this objective function that we chose here, it works, right? And so in a sense, we get a solution that at least intuitively, when you say it out loud, kind of makes some sense, right? And so, because generally speaking, your muscles want to avoid doing an excessive amount of work, and so choosing the solution that produces the least amount of total force, that seems to make sense, right? But this result here is actually not consistent with reality. Because in reality, right? Whenever you have a complex motion or your body exerts a load, right? It's usually not just one muscle that does all the work, right? Your body wants to balance that load amongst all the different muscles, right? Because if your body kind of always did things like this, you'd have certain muscles in your body that would tire out very quickly because they're doing all the work. Okay, and so in reality, whenever you're performing a motion or you're doing any kind of action, your body wants to kind of balance that work amongst the muscles as much as possible, so that everyone's kind of contributing their fair share. Okay. All right, and the way that your body does this is that instead of minimizing the total force, what your body aims to minimize is the power expenditure or the energy expenditure needed to produce a certain action. Okay. Okay. And so the question now becomes one of load balancing instead of, well, I guess technically the other one's load balancing as well, but we're balancing the energy load between the different muscles. Okay. Okay. And so what this means is that, if we were to kind of really run this optimization a little bit more realistically, we would have to change our objective function to reflect this objective. Okay. Because now our objective is no longer minimizing the total amount of force. What we want to minimize instead is the total amount of energy. Okay. So there's lots of ways that we can do this. I'm going to show you kind of the general simplest way. This kind of objective function, it's not universal, and so there's definitely better ones out there, but it'll definitely give you a much better result than the previous one that we have. Okay. So we want to incorporate energy into our objective function in some way. A good way or a good surrogate for energy is to take a muscle force and just square it. Okay. So if you just take your muscle force and you square it, do something simple like that, that's a pretty good indicator of metabolic energy consumption. Okay. It seems very simple, but let me kind of illustrate it like this. Okay. And let me kind of compare it basically to what we had before, which is just force, the force just by itself, right? So in our previous objective function, we had the force by itself, right? It was essentially like a linear scaling of the muscle force. Okay. So let's look at it like this. And so in the linear scaling, in the previous objective function that we had, if we double the amount of force, right? And so we take our muscle force and we double it, right? Because of the linear scaling, the cost associated with doubling the force will double the cost, right? Okay. And this was pretty much even across all the muscles, right? And that's essentially what linear scaling will do. So you double the force, you double the cost. Okay. Whereas for the squared scaling or the quadratic scaling, if we double the amount of force, right? And so if we compute basically 2f squared, okay? The cost that's associated with this is 4f squared, okay? And so when we double the force, there's a dramatic increase in the cost. So instead of doubling the cost, we multiply the cost by 4x. Okay. And so what this basically means that, in order to have a single muscle kind of exert more and more force, it's going to cost that much more. And so what this is going to incentivize is proper load balancing so that each of the forces don't get too high. Right? Because a solution where the gastrocnemius does all the work, that's going to have an insane amount of cost because, as we increase the gastrocnemius force, right, that 2,500 becomes squared, which is long. Okay. Okay. So that's roughly how metabolic energy consumption works in the body. So it's roughly F squared. It's not exactly F squared, but it's much closer to that than linear. Okay. And so that kind of gives us a hint of what our new objective function is going to be. Okay. Okay, so all these are going to be squared, but to ensure that each term is kind of normalized, okay, we're going to divide each term by its maximum. So we're going to have FG divided by FG max, and so that's going to be quantity squared plus FT divided by FT max quantity squared plus Fs divided by Fs max quantity squared. Okay. All right, so this objective function kind of accomplishes two things. So on the one hand, we can see that we have all the forces squared, right? And so that's going to make it so that our cost or objective function scales by the metabolic energy consumption. So that's what we want, okay? And the fact that we're dividing each of our variables here by a number, this is basically going to allow us to normalize our result across different variables, okay? Okay. So this normalization, it's a pretty common tactic, in optimization in general. Usually it's for cases when you're comparing different results with different units in the same function, right? And so in order for the units to match up, you have to normalize it. But for here, even in a case where all of the contributors to the objective function have the same units, it helps to kind of balance kind of everything out. So it's kind of another kind of balancing agent. Okay. Okay. All right, and so we're just about out of time, and so I want to leave a little time for you to get back to your exams too. So we'll go over the MATLAB implementation for this next time. But if we were to run this in MATLAB, what you're going to see is that this produces a much different result. Okay. And so it's going to produce a result where Fg is going to be equal to 820.41 newtons. Ft, we're going to have an optimal result of 93.46 newtons. Okay. And Fs, now Fs is going to be one doing most of the work because it has a much higher maximum. Fs is going to be 1868.2 newtons. Okay? So this objective function combined with our design variables and our constraints does a much better job of kind of balancing the load in between the muscles relative to what the muscles can do. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's it. So I have your exams here. So if you are here in class, you can come pick it up. I'll bring the exams again on Wednesday, and so if you weren't able to come today, you can pick it up then. So once I get back to my office, I'm going to send out the schedule for the final presentation. So make sure you keep an eye out for that email, right? So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Wednesday.
Sure.
You guys are presenting next week for this. So during the last week of lectures. Yeah. So the first presentations are going to be a week from today.
I can keep it. Yeah, we can keep it.
Yeah, you keep it. Mhm.
Thank you.
No, we're not meeting during finals week. So I usually do office hours by appointments during finals week. But if there's enough people that want to meet during finals week, I may just open up general office hours. My schedule is a little bit different during finals week because that's when I do kind of like more graduate student stuff for like project defenses and meeting with potential students and things like that. So my schedule is a little bit different, and so I usually need to make a different office hour schedule for the final week. Yeah.
Oh, yeah, fine.
All right, Zoom, any final questions before I wrap it up? All right, see you guys.